Welcome everyone to the fifth seminar of this year's Australian Institute of Physics Theoretical Physics Seminar Series. I'm David Tilbrook from the Department of Fundamental and Theoretical Physics at ANU, and I'd like to start as always by acknowledging the people of the Ngunnawal Nation on whose traditional lands we, ANU and most of all of Canberra and some of New South Wales sits. And of course, we acknowledge the traditional custodians of lands all around Australia. In the last talk, we heard from Dr. Stefan Rochelle from the University of Melbourne, who talked about simulations of time crystals on a quantum computer. If you missed that talk and you'd like to see it again, it's available on the AIP YouTube channel, as are all of the seminars for this year's seminar series and also for last year's seminar series. Today, we are going to hear about matters related to one of the most significant unsolved problems of classical physics, that of the properties of laminar and turbulent flow and things that are related to that, although I don't know exactly what Nigel is going to be speaking about. This is well known to be a major problem, of course. One aspect of it, the solutions and existence of the properties of the solutions and existence of the solutions of the Navier-Stokes equation, of course, is a subject of one of the Clay Mathematics Institute's $1 million prizes. So you might want to listen attentively. You might get the information you need to win $1 million. You never know. So as I was saying to Nigel before the talk, my first exposure to this was this area of physics happened many years ago when I was asked by a small company that was designing heat sinks for electronic systems, these things that you bolt transistors onto in order to get the heat away from them, who wanted to know why the performance of their heat sinks had decreased when they increased the number of fins. And what should they do? Should they put flutes on the fins or not, or put ripples, or how far apart should the fins be, and so forth. And after some time and a bit of theory and a bit of experimental work, we managed to work out a kind of optimal number of fins, which was pretty good because I didn't know very much about the subject. But, and I'm sure I would have been able to do a better job if I had read more widely on of the works of today's author. But we managed to muddle on nevertheless. So it's a great honor and privilege to introduce our speaker for today's seminar, and there is no better person to speak on this whole area of physics than today's speaker, Dr. Nigel Goldenfeld. Professor Goldenfeld has made a lot of very significant contributions to a wide area of physics, pertaining to applications as wide as geology, biology, epidemiology, astrophysics, entomology, and more generally to the properties of emergent and collective phenomena. Professor Goldenfeld did his PhD in the undergraduate and his undergraduate degree in the University of Cambridge, and is the author of one of the standard graduate texts on statistical mechanics. I have a copy in my library here, and it's well worth getting if you ever need to do any work in statistical mechanics, or if you haven't studied it in your postgraduate experience. He is a fellow of the American Physical Society, a fellow of the American Academy of Arts and Sciences, and the recipient of the 2020 Leo P. Kadanoff Prize of the American Physical Society. His talk today is entitled The Life and Death of Turbulence. Over to you, please, Nigel.
Thank you very much for inviting me. It's a pleasure to talk at such a long distance. I'm sure I'd enjoy it even more if I were there, but we'll have to do what we can. So as David said in his introduction, turbulence is widely considered to be the perhaps the hardest and greatest unsolved problem of classical physics. And in this talk, I want to ask the question, what would it take to actually solve the problem? How would we know if we had done it, and what would the implications be? And I'm not a believer in the formulation of the problem as posed by the Clay Foundation. So I'll say that right out the bat. If you want to ask me questions about why at the end of the talk, you're welcome to do so. But I think after you've heard what I have to say, you'll probably understand my perspective better. So my perspective is essentially that to understand turbulence, we really need to be thinking about statistical mechanics, not necessarily partial differential equations, at least in its classical form, and I'll explain why as we go along. So let me first start off by acknowledging my collaborators. I'll explain what the life of turbulence means later, but my collaborators are these people here, and I'll show you them at the end. And the depth of turbulence is the laminar-turbulent transition, and this is a long standing collaboration now that's been going over for me over 10 years, and particularly involving the people you see here. I particularly want to point out the experimentalist Björn Hoff, who you'll hear about, and then my students Hongying Shi, Songlin Se, and Xie-Ying Wang. So let's get into it, and let's start with some propaganda. So of course it's necessary in a physics talk to have some quotes from Richard Feynman, so we may as well get it over and done with. And in fact, Feynman actually said some very important things about turbulence, and I want to highlight them here, not just as out of a sense of duty. So this is the Feynman volume 2, and he's just derived the Navier-Stokes equations, and this is what he says. He says, we've written the equations of water flow. From experiments, we find a set of concepts and approximations to use to discuss the solution: vortex streets, turbulent wakes, boundary layers. When we have similar equations in a less familiar situation, and one for which we cannot yet experiment, we try to solve the equations in a primitive, halting, and confused way to try to determine what new qualitative features may come out, or what new qualitative forms are a consequence of the equations. Now, you'll notice that I've highlighted the word qualitative because Feynman is the epitome of the quantitative physicist. Of course, he got his Nobel Prize for the theory of quantum electrodynamics, where we can compute quantities to 12 decimal places and they agree with experiments. It's unprecedented. But what's concerning him here is the qualitative features of the equations. And he goes on to say, the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today, we cannot. Today, we cannot see that the water flow equations contain such things as the Barber pole structure of turbulence that one sees between rotating cylinders, and then, which is called Taylor-Coetz flow. And then he goes on and talks about Schrödinger's equation, frogs, and so on and so forth. So that's the Feynman quote for today. And the point I want to make is that when you ask a question about the qualitative nature of matter, you're asking about what we call in statistical mechanics the phase diagram. And so what our goal in this work was to try to understand the qualitative content of the equations of fluid mechanics, particularly the phase diagram, and in fact to see and quantify in a universality and scaling laws in turbulence, and indeed there are many. So we have made a good start on this. I'm going to show you two problems. One is on transitional flows, and one is on what are called fluctuation-dissipation relations far from equilibrium, where we make novel predictions and perspectives based on statistical mechanics. And we've done the experiments to test those things, and it works. And I don't know any other way to make those predictions other than to use statistical mechanics. So let's get started. And we'll start off, as ever, with a bunch of particles bouncing around in a box. And as everybody knows, if you just do deterministic and Newtonian mechanics of many particles in a box, just stick it on the computer, you very quickly see that you get the results of statistical thermodynamics, and that's very simple to see. Okay, so then you say, well, let's have an infinite number of particles in the box. So if I have an infinite number of particles in the box, then I've got a field, and that field obeys the Navier-Stokes equations for the coarse-grained velocity field U, as shown here, where we have Newton's equation F equals ma plus a dissipation from the viscosity, and it comes in this way over here. This equation here describes the incompressibility. So just because we've gone from a finite number of particles to an infinite number, it shouldn't surprise you, perhaps, that this also will obey statistical mechanics. But in this case, it's non-equilibrium statistical mechanics, and we'll see why that is in a few minutes. So the phase diagram of turbulence, at least in its simplest form, is governed by the control parameter known as the Reynolds number, which is the characteristic velocity of the fluid, the characteristic dimensions of the system, divided by the kinematic viscosity. And the kinematic viscosity is just the molecular viscosity divided by the density. So the point about this is that if the viscosity is very high, such as a very viscous fluid like honey, then the Reynolds number is very small, and you get a laminar flow, which is steady and predictable. On the other hand, if the velocity is very high, say u is very large or nu is very small, then what happens is you get turbulence, as shown over here on the right. And these numbers here are the numbers appropriate for pipe flow, and somewhere around 2000 is the laminar-turbulence transition shown here in this picture, where you've got a wind farm, where you can see turbulence being generated behind the propellers here. So we want to understand the different regimes in this diagram here. And this regime here, where as you go down in Reynolds number and turbulence disappears, I've called the death of turbulence. And this regime over here, where turbulence is just ongoing and fluctuating and unpredictable, is what I mean by the life of turbulence. So one thing you're going to notice about this, this diagram is that I've eschewed the usual conventions of theoretical physics. In theoretical physics, what you try to do is, wherever possible, you make the system be homogeneous, be three-dimensional, have periodic boundary conditions. Here, we're not going to do that. Here, we're going to not have periodic boundary conditions. And the reason is this: turbulence is fundamentally about instabilities. It's not about noise, it's about instabilities. And symmetry is the enemy of instability. So what happens is turbulence is generated by an incoming flow coming in these pictures from the left, and then something happens, and then what happens is you get either some linear long wavelength disturbances causing turbulence, or some nonlinear spatially localized disturbances causing turbulence. And so you get a transition to turbulence. In the former case, it's a supercritical transition typically. In the case that we're going to be interested in this flow, the transition is nonlinear, spatially localized, and is a subcritical transition. And I'll say more about that later. Now, the other thing is you'll see is that there's a mean flow that is imposed, but turbulence itself can create mean flows, emergent mean flows, and those, of course, react back on the imposed mean flow. So you have a very complicated set of mean flows, emergence, fluctuations, and all of that. Now, what does it mean to solve turbulence? How would we know if we'd solved it? So let's suppose that you go down the street and you run into a condensed matter physicist, and you ask her, well, what would it mean to solve turbulence? And what you might say is, well, turbulence is all about fluctuating velocity fields, so why don't you predict for me the fluctuation spectrum at small scales where the fluid is fluctuating? And so let's go and explore how one might do that. So what happens is when you create turbulence by sort of putting your fingers in the bathtub and swirling them around, you create these swirly whirly eddy things, and they spin off other smaller swirly whirly eddy things, and so on and so forth. And that process is not a viscous process. It's not the eddy breaks down due to viscosity, like the wheel or the chain coming off your bicycle as you cycle along. This is a Hamiltonian process. This is actually just what they do. And so what happens is they spin off smaller and smaller scales, smaller and smaller eddies, and so you get what is called a cascade, going to smaller and smaller scales. And this process, turns out, it was a guess by Richardson and Kolmogorov, doesn't involve friction. And so that means that viscosity, in some sense, should not enter into the equations. So then this picture is that at small wave numbers, large length scales, you're feeding energy into the system. The energy cascades without loss of energy down to a small scale, where eventually molecular viscosity kicks in and you get Joule heating. Okay, so that's the qualitative picture. Now, it was Kolmogorov in 1941 who came up with a brilliant argument that made an actual prediction about this. So what he said was, let's have a look at the energy per unit wave number range K, that's E of K, we'll call that the energy spectrum. That's got to depend on K, it's got to depend upon the rate at which you're feeding energy into the system, it's got to depend upon the viscosity, the kinematic viscosity, and it depends on the size of the system. Now, out of these quantities here, you can do dimensional analysis and you can construct a length scale, which is known as the Kolmogorov scale, which I've shown you here. Now, then, once I've created these dimensionless groups, what I have is the following. E of k must be a function like this. It's got to be nu squared over eta, and that has the dimensions of E of k, and then a dimensionless function of wave number times this length scale, eta k, and then wave number times the system size L. And that's all that dimensional analysis tells you. Now, what we do then is we make an approximation or an assumption that in the Russian mathematical physics literature is known as the assumption of complete similarity. So namely, what we're going to assume is that as we make the system size go to infinity, but keep the wave number fixed, so that's one way that you can make the Reynolds number go to infinity, we assume that there's complete similarity and there's no singularity in this parameter. So what that means basically is that I just simply replace KL by the number infinity. Okay, that's fine. The next thing we're going to assume is that, let's go back a second. The next thing we're going to assume is that we now may take the Reynolds number going to infinity limit another way. We simply let nu go to 0, the viscosity going to 0, keeping k fixed. So that means k eta goes to 0. So that means k eta here is now naively replaced by 0. But not so fast, because nu appears outside here, nu is inside eta through this relation here. And so what's got to happen is that as I take this limit, nu goes to 0, there has to be a fortuitous cancellation of nu outside this function and inside this function. And that can only happen if this function is a power law. So you go and work out what power law that is, and it's a couple of lines of algebra to see that what you end up with is that E of k has to go as epsilon to the 2/3 times k to the minus 5/3, so that this limit doesn't give you either 0 or infinity. And that is Kolmogorov's famous 5/3 law. So what this tells you then is if I look at the energy spectrum as a function of wave number, it's going to start off at small scales going as just k squared. Then you have this regime here where it goes as the so-called inertial range, where it goes as k to the minus 5/3. And then eventually at high wave numbers, small length scales, you have dissipation. And in fact, when you think about it more carefully, you'll see that the size of this inertial range, where you have this power law behavior, depends on the Reynolds number. And as the Reynolds number goes to infinity, the size of that regime gets larger and larger. So the only thing that's wrong with Kolmogorov's argument is that it happens to be wrong. And it's wrong because this assumption of complete similarity in this variable turns out not to be correct. In fact, you have the phenomenon of large-scale intermittency, which basically means algebraically that as I take the limit KL goes to infinity, this function doesn't go to a constant. It just scales as KL to the power eta, where eta is some anomalous exponent. Okay, so you can't just simply replace KL by infinity. It's an asymptotic process. So then when you go through the whole argument, what you end up with is the same thing as you had before, but now k to the minus 5/3 is modified by KL to the power eta. And so you have a different scaling law. And this eta is known as the intermittency exponent. And we'll say more about that towards the end of the talk. Now, let's suppose you carry on walking down the street and you run into an engineer. And you ask the engineer, well, what would it mean to you if we could solve turbulence? Well, the engineer says, well, look, I'm trying to design a gas pipeline, or I'm trying to design an airplane or a car or something like this. I want to know what is the dissipation, the frictional drag experienced at large scales. That's what I care about. So this was measured in pipes by Nikoradze in 1933. So what he measured was a thing called the dimensionless friction factor, which I'll define later in the talk, but it's basically just the pressure drop across a pipe. And he did this in pipes that were rough, and he varied the roughness of the pipes, or at least the ratio of the roughness of the pipes to the diameter of the pipes. The smoother pipes had, of course, the lower friction factor. And what I want you to see from this graph here, which we'll come back to at the end of the talk, is that it's a fairly complicated drag profile as a function of the Reynolds number here. Okay, so that's a measurement, but can we understand anything about this theoretically? And we'll see we can at the end of the talk. So then you might say, well, that's all great, but somehow these two things should be connected. So can we use our understanding of what happens at small scales with the fluctuations in the velocity field to predict something about the friction experienced in rough pipes. And that question is posed here. I'm going to show you that the answer to that is yes. And of course, on this side of the picture, we have fluctuations. On this side, we have dissipation. And so this is something like a fluctuation-dissipation relation, which you may well be familiar with in equilibrium statistical mechanics, but certainly much more complicated in non-equilibrium statistical mechanics. So then you might say, well, okay, that's all great, but I want to know, when does a fluid actually become turbulent? And so the question is, can you predict when and how fluids become turbulent? And that's the problem that I want to start off with. So here is Reynolds, who did the first scientific investigation of the transition to turbulence in a pipe in 1883. And what he did was he took a pipe, he injected fluid into it, he put a bit of ink in the fluid, and so you could see from the ink profile, the streamlines, what the nature of the fluid flow was. At low speeds, the flow was smooth and regular and laminar, as sketched over here. At high speeds, the flow after initial transient became ragged, jagged, and irregular and turbulent. And in between, there was this transitional region where you'll see something strange. The flow becomes turbulent, but then goes back to laminar over here, then turbulent, then laminar and turbulence and so on. And he called these little regions of turbulence flashes. Today, we call them puffs. And this is one of the reasons why this problem is so hard. Now, if you look at the pictures I just showed you, you might ask yourself the following question. Well, if I ask how much turbulence is in the pipe, that turbulence fraction is going to depend on the Reynolds number. And here are the actual data for that. And you can see that there's a curve that comes up like this. And I'm sorry, there's some shouting in the background. I think my dog has just killed a skunk. So very sorry about that. All right. So one thing I want you to notice is that the way that the turbulence occurs is spatially non-uniform, these rare sharp bursts of turbulence, and that's one of the things that makes this problem complicated. All right then. Now the things I've shown you so far ought to remind you of what happens at phase transitions. So you might look at this graph here for how much turbulence there is in the pipe. And you might say, well, this looks like how the order parameter varies as you go through a second order phase transition. Similarly, you might have a look here at the energy spectrum, which you can see defined over here. It's basically the velocity order correlation function. And you might say this is in inertial range at least, is power law correlated fluctuations, which again is reminiscent of a continuous phase transition. So there seems to be some possible connection between them. I want to explore that in the next couple of minutes by asking the question, why has this problem taken so long to solve? So why is turbulence so hard to solve? And to answer that question, I'm going to ask an easier question, which is why are phase transitions hard? So in phase transitions, what you have is you have systems which have got strong interactions, strongly fluctuating order parameter. Those fluctuations are non-Gaussian. They are strongly intermittent. But what makes the problem hard is that there is no usable small parameter. So here I've shown you the Landau free energy near a second order phase transition. And you might say, how can you say that there's no small parameter? Obviously, there's a small parameter. Look, we're looking very close to the critical temperature. T minus Tc over Tc, as I get closer to that, is getting smaller and smaller. But if you look on page 191 of any good textbook on the normalization group and critical phenomena, you'll see that after you've done dimensional analysis on the field theory describing the system, what ends up happening is that the fluctuations are coupled through this dimensionless parameter here, which involves T, the reduced temperature, to the power d minus 4 over 2. And what that means is that if you're below 4 dimensions, this parameter goes to infinity and not to 0. So the coefficient of the interaction becomes relatively large as you go to the phase transition. So there's no usable small parameter. When we look at turbulence, it also has strong interactions and velocity fluctuations in velocity derivatives. They're non-Gaussian and they're intermittent. And again, there's no small parameter, which is usable. Here's the Navier-Stokes equations I showed you before, and you can see the only nonlinearity in the problem is this advection term over here. And as I send nu to 0, this coefficient here stays to be 1. So the coefficient of the nonlinearity gets arbitrarily large as you go to the infinite Reynolds number limit. Now, now you can see that there's a connection between critical phenomena and turbulence. Let's ask ourselves the following question. Can we understand turbulence by following the route that led to the solution of the problem of phase transitions? So how was the problem of phase transition solved? Well, Ken Wilson got the Nobel Prize for developing renormalization group theory. And that in turn was based on Leo Kadynov's block spin and scaling ideas, which he worked out in 1966. And they really were built on the findings of Ben Widham, who discovered data collapse about the same time. And these were sort of independent discoveries. So now we're going to ask, first of all, does turbulence exhibit critical phenomena at its onset? And then at the end of the talk, I'll ask, can we see some of the signatures of critical phenomena in fully developed turbulence? Okay, so today, when we look at the transition to turbulence, it's measured in a similar way to the way that Reynolds did in 1883, but it's done in a statistical way. And I'm showing you a picture from a seminal paper by Björn Hoff in Phys. Letters 2008. So what you do here is you take a pipe, you have a flow going through it in a very steady way, and it's controlled very carefully so that the flow is actually laminar. So the laminar turbulence transition in a pipe is subcritical. The laminar flow is linearly stable, and so you can make it to stay stable, to stay laminar up to Reynolds numbers of 100,000. But actually, turbulence really has a transition at a Reynolds number of about 2,000. So then what you do is you inject a disturbance, a little bit of fluid in here, which creates some turbulence. That turbulence floats down the pipe. It creates drag as it does. And then you can ask the following question. When you know how fast the fluid is flowing, you know how far it's got to go. And so you ask the question, does the turbulence live long enough to get to the end of the pipe? So remember, the fluid is in a laminar state. So what happens is the turbulence is floating down the pipe, and sometimes it might, if the Reynolds number is too small, it will just die away. And sometimes it will just live long enough to get to the end of the pipe. If it dies away, then the fluid will come out of the pipe following the yellow trajectory faster. And if the turbulence is still there, it imposes extra drag. And so the fluid will come out following the red trajectory. So you just ask the question, did it follow the yellow trajectory or the red trajectory? Yes or no? And then you do this hundreds of thousands of millions of times in a very carefully controlled flow. And you can then estimate the survival probability of turbulence as a function of Reynolds number and as a function of time. So let's have a look at the data. So here's the Reynolds number along the horizontal axis here. And now we're in the regime somewhere around 1800, 1900, 2000, something like that. Here, a puff is metastable, meaning if you create that puff, it'll live for some period of time and then will eventually decay, as shown in this computer simulation here, where the color tells you the turbulence intensity. The survival probability is shown over here. This is the logarithm as a function of time for different Reynolds numbers. And you can see that that survival probability is an exponential function with a lifetime tau, which is a function of Reynolds number. That lifetime tau is plotted on a semi-log scale over here, Reynolds number versus the logarithm of tau. And you can see that the data fall on this upward curving curve like this. And so what we see from that is that the lifetime increases faster than exponential. Now, when you go to higher Reynolds numbers, what happens is as you go to higher and higher Reynolds numbers, you eventually expect that the flow will become turbulent. But what happens here is that the puffs actually split into two, and you get and then those puffs themselves can split into two and decay and so on and so forth. And so you get a very complicated spatial temporal pattern. And you might ask yourself the question of how long it takes for a puff to split. Well, obviously, the higher the Reynolds number, the shorter that time will be. And so when you go and measure it, what you find is that the mean time between splitting events follows this curve over here. And again, this is upwardly curving. So you might say, well, let's take a double logarithm of that lifetime. And I've shown you here, you can see that the data fall on these two straight lines and they intersect at this Reynolds number here, which you can interpret as the transition to turbulence. Because above this Reynolds number, puffs will always split. And so at long times, you'll always have some fraction of turbulence in the pipe. So what I've just told you is that all the characteristic time scales of turbulence scale super exponentially as e to the Reynolds number. And later on, I'll explain to you where that functional form comes from. Now let's build a theory for the laminar turbulence transition. And we're going to build the theory based on what we do for phase transitions in equilibrium statistical mechanics. So let's remind ourselves what we do for magnetic systems. So in a magnetic system, we start off at the lowest level of description with the electronic structure. And of course, that's impossibly hard to solve. So then you try to just make an effective theory for the electronic dipole moments, the spins. And so you get an Ising or Heisenberg model. But that's too hard to solve unless you're in 2 dimensions. It's an Ising model. There's no external magnetic field and your name is Onsager. Other than that, you can't solve that. So that's too hard to solve. And so, so then what you do is you make a sort of coarse-grained free energy known as the Landau free energy. And from that, you can then work out the renormalization group universality class. And so the predictions that one makes here are recapitulated on this slide. Here is the magnetization as a function of temperature. As you in zero field, as you go below the critical transition, the magnetization rises. Here, the statistical mechanics is dominated by weak infrared long wavelength modes, and the magnetization goes as the reduced temperature to some power beta, some singular limit. On the other hand, if you sit at the critical temperature itself and measure what happens to the magnetization as a function of external magnetic field, normally you would expect linear response theory to apply. But at the critical point, that breaks down, and the magnetization depends on the external field to some non-unit power, like this. And what Widom discovered was that these stylized facts follow from a similarity formula shown over here, where in fact it's just really a function of one reduced variable like this. And so here are the data for 5 different magnetic materials, plotted the magnetization scaled in the way that theory predicts, temperature scaled in the way that theory predicts, and all the data fall onto one curve, and that curve is the solid line here, which is the renormalization group prediction with no adjustable parameters. So this is really great because it shows us that our model has given a precise prediction in agreement with experiment. But in fact, it's a bit misleading because this isn't actually a model at all. It's a model of a model of a model of a model of a model that gives you the precise prediction. It's a model that starts off with quantum chemistry and then goes to electronic structure, and then say a quantum Ising model or quantum Heisenberg model, then classical, and then finally Landau theory. And every step along the way here is a completely unjustified, non-systematic approximation. And nevertheless, even though you can't justify any of these approximations a priori, they end up giving a precise prediction, and that's due to relevant variables and things like this, which you can read about or probably know about from statistical mechanics. So now when we come to turbulence, what we want to understand then is not the analog of electronic structure, the kinetic theory, or the coarse-grained model, say the Ising model, which is the Navier-Stokes equations. What we want to understand is what is the analog of Landau theory and what is the renormalization group universality class to understand the laminar-turbulent transition itself. So of course, we don't know how to calculate anything. So what we did was we looked at numerical simulations to try to see if we could find long wavelength collective modes at the laminar turbulent transition. And the answer was that we could. What we discovered by simulating a single puff in a pipe, a 20 diameter pipe, which could just contain one puff, is that at small scales, indeed, you get turbulence, but there's a large scale as you move your mode, which is shown over here, which is independent of the in the Z direction over here, but scales, but varies in time and varies with radius as shown over here. And the important thing is that the energy of the modes oscillates in time with a phase shift. And what's actually happening here is that the anisotropy of the turbulence at small scales is creating a mean flow in the azimuthal direction, and that mean flow is then shearing the turbulence and isotropizing it. And from the momentum balance equation, you can derive this equation of motion for the azimuthal flow, and you can see it's driven by the radial gradient of the velocity fluctuations. This is the Reynolds stress tensor. So what happens is the mean azimuthal velocity decreases the anisotropy of the turbulence, decreases this thing, and that suppresses the turbulence. So in other words, turbulence induces a flow, I'll call it a zonal flow, and that zonal flow then suppresses the turbulence that created it. Well, once the turbulence has been suppressed, the zonal flow goes down, and now there's nothing to suppress the turbulence, so the turbulence then gets activated again. And this is exactly what happens in a predator-prey ecosystem, an example of an activator-inhibitor dynamical system. So now we're going to look at the idea then that pipe flow near the transition to turbulence can be thought of as two modes which are activator-inhibitor-like. So in a sense, it's like a predator-prey ecosystem, which of course also has population cycles with a phase shift of pi by 2. So let's explore that idea. So how would we model a predator-prey ecosystem? Well, what we would do as a statistical mechanician is we'd say the predators are A, the prey are B. They live in an environment where there's a food source or space, which we'll call E. And what happens is these things sort of diffuse around, and every time they meet, something happens, or they may just produce babies or whatever. So here, for example, is the prey eating some of the food and producing baby prey. Here is something more interesting. A predator A meets the prey B, and with some probability P, eats the prey, uses the energy thus obtained to make another baby predator, and so you end up with two predators. And this series of reactions, including death and the competition, is a stochastic description of an ecosystem. And when you understand this mathematically, it gives you the oscillating population cycles that you see in real experimental data, unlike the differential equations, the Lotka-Volterra equations that you might have read about in an ecology textbook. So I'm now going to show you that the Landau theory for transitional pipe turbulence is a stochastic predator-prey model. And to do that, we're going to remind ourselves that once we write down the Navier-Stokes equations in terms of interactions between different types of waves, different types of flows, we can actually formulate that in terms of Feynman diagrams, as my colleague at Illinois, Bill Wild, did in the early 1960s. So the Navier-Stokes equations have a quadratic nonlinearity. So every vertex here is a triplet vertex. So what we do then is we say we've got two modes. The zonal flow is one mode, the turbulence is another, and we write down all possible diagrams that you can write down. And for each of these diagrams, you can see that there is a predator-prey interpretation, if you like, wave-particle duality. Let's have a look at this diagram here. This says turbulence encounters a zonal flow, something happens, and out comes two zonal flow lines. That's just the reaction that I told you before. A plus B goes to A plus A. So now we can look at this stochastic predator-prey ecosystem, and we can ask, what does it tell us? What can it predict for us? I'm going to show you now that it predicts the phase diagram, the lifetime statistics, and enables us to understand the universality class of the laminar-turbulence transition in pipes. So here is the phase diagram that I've already shown you, pipe flow turbulence, and with the Reynolds number, and here is the phase diagram for this stochastic predator-prey model. Remember, the stochastic predator-prey model knows nothing about the Navier-Stokes equations. It is just literally simulations of those chemical reactions, if you will, that I just showed you. So what is the analog of Reynolds number? Well, it's the prey birth rate. So why is that? Well, think about this. Let's suppose you've got wolf and sheep as your predator and prey, And let's suppose the sheep reproduce every 100 years. So basically what the wolves will do, they come along, they'll eat all the sheep and everything dies. That's with a small prey birth rate. On the other hand, let's suppose the prey birth rate, the sheep reproduce every 10 minutes. Then the predators are wandering around eating the sheep, but the sheep are busy popping up babies. And so you end up with a situation where you can envisage that there would be a coexistence of the two things, and you would get these predator-prey oscillations. Well, that's exactly what happens. What we simulate here is a spatially extended system. So it's not just at one point in space, but these particles can hop around and move. And so we simulate predator and prey in an ecosystem shaped like this. And what we find is that for small prey birth rate, you have an instability and a puff of predator and prey is a population that will eventually die, mimicking what you see here for a decaying single puff. On the other hand, as you increase the prey birth rate, what happens is the population undergoes a pattern-forming instability and splits into these two traveling waves here, just like what you see over here in the turbulent pipe. And here's the world lines of the system in the splitting machine. So here on the right is time on the vertical axis and space on the horizontal axis, and the color is the turbulence intensity. And you see this sequence of puff splitting events. Here, we're looking at the predator-prey ecosystem. The color now is the intensity of the prey, because it's the prey that represents the turbulence. And you see again that the population undergoes these sequence of splitting events, just as we see over here. But it's not just that the pictures look the same. We can also measure the statistics of the extinction time in the decaying case and the time between population splitting events in the spatiotemporal intermittency case. And when you go ahead and do that, this is what you find. Here on the right-hand side is the data I already showed you from Hoff's turbulent pipe experiments. And here on the left is the results of computer simulations of the stochastic predator-prey ecosystem, showing you the lifetime for decay and for splitting. And again, you see that this recapitulates precisely what you see in the real fluid turbulent experiments. So what we've just learned from this is that the death of turbulence, as you go from turbulence to laminar, is the extinction transition in the stochastic ecosystem. Now, what we're trying to understand is the universality class of this transition, assuming that it's some kind of second order phase transition. And I'm going to show you that it is. Now, what I've shown you so far is that we start off with classical turbulence. Near the transition, it reduces to a kind of two-fluid model, as shown over here. That two-fluid model is in the predator-prey type. But the thing we want to understand is, what is the universality class? I'm going to show you now that that universality class is directed percolation. And we're going to see that because if I take the stochastic predator-prey model, write it down as a functional integral, and then work out what happens near the transition, you see that that functional integral turns into Reggian field theory, which can be mapped into directed percolation. Now, I'm not going to show you this using field theory. I'm going to show it to you diagrammatically in a very simple way. So the idea is the following. Let's suppose that I have a granular material, a porous medium, if you like, and there's a certain probability P of fluid flowing through and being able to go from one occupied site to one further down. You can think of the time direction as being fluid flowing under gravity. Okay, so this is one space and one time dimensional directed percolation. You can think of this as your coffee, water going through the coffee grinds in the morning as you make your coffee. If you look at the trajectories here that the fluid can take, you can easily convince yourself that all of the possible paths can be made up from these four basic diagrams here. The top one tells you what happens at time t, the bottom one tells you what happens at time t plus 1. And here you can see fluid doesn't get through to the next site, the fluid gets through to these two sites below it, the fluid hops diagonally, or the fluid goes from two sites into one site. And these are the names of the different processes. Okay, so when you simulate that process, what you find is that if the probability of percolating through to the next layer, P, is too small, then nothing actually happens at all. On the other hand, if the percolation probability is high, then at long times, you'll get through to the other side. You'll have many occupied sites at large times. And somewhere in between is a transition where the number of occupied sites, which in this case corresponds to a fraction of turbulence, is arbitrarily small. And in fact, that density, that turbulent fraction, scales as P minus PC to the power beta. And there's other critical phenomena that I'm not going to have time to tell you about. So this is what you see then, directed percolation in 3+1 dimensions in a pipe. You start off with a puff, and then the puff gradually disappears, as shown over here. If I looked at a one-dimensional cross-section through it, I'd see these initially occupied sites here, and then eventually the pixels die away until eventually the last gasp that you can see over there is this pixel, is this trajectory shown over here. So what's happening then is that the active state, the turbulent state, persists until the most long-lived of these percolating strands decayed. In other words, the lifetime of turbulence is related to the longest, the probability distribution of the longest path of these independent, randomly percolating paths. And that means it's governed by extreme value statistics. Now, extreme value statistics answers a question which is something like the question of the central limit theorem. In the central limit theorem, you say I've got a bunch of random variables which are independent, identically distributed perhaps, and if I add them all up and look at the average, how is that distributed? And of course, the answer is you get a Gaussian or something like this. Okay. Extreme value statistics says take these random variables and take the maximum of them and ask how is that maximum distributed? Well, this was worked out by Fisher and Tippett in 1928, and the relevant distribution, there's three of them in fact, the relevant one for us here is what's called the Fisher-Tippett-Gumbel distribution, whose cumulative distribution function is e to the minus y. In other words, this extreme value statistics is fundamentally the reason for the super exponential scaling of lifetimes that I showed you at the beginning. Now, if I write down the basic predator-prey processes on a space-time lattice where I and J represent lattice sites, I get a set of reactions shown over here. Now, near the transition to prey extinction, the prey obviously population is very small. The predator live off them, and their population is equally small. So, to an approximation, we can say that the predator will just set them equal to 0. So we wipe them out. And now we've gone from a 3 trophic level ecosystem: predator, prey, and the food. The food is the kinetic energy of the laminar flow. The prey is the turbulence. The predator is the induced emergent mean flow, the zonal flow. Now we've taken away the predator, and now we just have these, the food E and the prey B. These are the reactions. And if I look at these reactions where I and J represent the lattice sites and write these things down diagrammatically, you see that what you have left are the 4 basic processes of directed percolation. And so what I've just shown you by this heuristic argument, which can be made rigorous, is that near the extinction transition, stochastic predator-prey dynamics reduces to directed percolation. Okay, so is this correct? What we're claiming then is that if I want to understand the transition to turbulence in the pipe, it behaves in the same way as particles hopping on a lattice, or if you like, water dribbling through your coffee granules in the morning. So Björn Hoff did a beautiful experiment a few years ago where he took Taylor-Corrett flow, that is two cylinders, coaxial cylinders, an inner cylinder and an outer cylinder. The outer cylinder rotates, the fluid is between them. And what happens when you do that is you get regions of turbulence, which are shown here in the black. The regions of laminar are shown in the silver. And what you do is you look, say, along this line here and record what you see as the fluid goes past. And you take these pictures, the first rotation, laminar-turbulent, 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 and so on. And the second one, same thing, but it's slightly different. Third time, slightly different, and so on. Take these pictures, stack them up one underneath each other, and you get the sequence of pictures shown over here on the right. This is for rotation speeds smaller than the critical Reynolds number, around equal to the critical Reynolds number and greater than the critical Reynolds number. And what you see is that at long times, you have a lot of turbulence in the system. At a small Reynolds number, at long times, you get no turbulence, and halfway in between, you get some turbulence. And then you can go and measure the turbulent fraction, and you get these data shown here, and you can fit these data over 2 decades of reduced Reynolds number, and it fits the predictions of directed percolation with an exponent 0.276. And just in the last couple of months, Hoff extended these data to 2 dimensions, to 2 + 1 dimensions, and again, it works very well. And it's not just the turbulent fraction, it's universal scaling functions and other things as well. What about predator-prey dynamics? Do we see that? Well, it's very difficult to observe that in a pipe, but you can observe it in magnetohydrodynamics and some electroconvection experiments in 2D. Here I'm going to show you data from a tokamak in Europe, where you have drift wave turbulence going around the tokamak like this. You have a zonal flow, an emergent mean flow going azimuthally like so, and Estrada et al. About 10 years or so ago measured the predator-prey oscillations, which had been predicted back in the 1990s by Pat Diamond. So what I've just told you then is that we predict that the laminar turbulence transition is a non-equilibrium critical point in the universality class of directed percolation, and this has been observed in 2 experiments. I'm not going to have time, I think, to go to what happens beyond the critical point, where you get slugs spreading. So this is puffs decaying, this is slugs spreading. What I'll just say, though, is that the same model that captures this, the stochastic predator-prey model, now extended to include puff-puff interactions through streamwise shear interactions, also explains the phenomenology of slug spreading, and that paper is coming out in Physical Review Letters shortly. So I'm going to skip this, and I will come back to it at the end of the talk if people are interested. So I want to talk now for the last 10 minutes about fluctuations and dissipation. Now, at the beginning of the talk, I told you, I showed you data from Nikaradze, who measured the pressure drop across a pipe normalized by the kinetic energy density rho u squared. And he did that by taking sand grains of a uniform size, gluing them to the sides of various pipes of different diameters, and so he could vary the pipe diameter, as shown over here. So the friction factor is plotted on the vertical scale here, Reynolds number here, these are both logarithmic. And of course, the smoothest pipes have the smallest friction, so they're down over here. The largest pipes have the greatest friction, so they're these curves over here. Now, what you can see happening here is that at small Reynolds numbers, below a couple of thousand, the friction factor scales as 1 over Reynolds number. Why is that? Well, remember the friction factor is normalized by the velocity squared. In other words, the Reynolds number squared. So what happens is if I have Stokes drag, which is the drag is just proportional to the velocity, i.e. the Reynolds number, and you divide by Reynolds number squared, then you get a friction factor that goes inversely proportional to Reynolds number. So that's this regime over here. Then we have the transition to turbulence, which is what I just explained to you over here, the drag catastrophe. And then you see the friction factor going down as you increase the Reynolds number. And the smoother the pipe is, the further down this line it goes before deviating from it. And this line has a slope of Reynolds to the -1/4. And this law, friction factor going as Reynolds to the -1/4, is known as the Blasius scaling law. Then something happens, this non-monotonic dip like this, and then finally at large Reynolds numbers, the friction factor is independent of Reynolds number, but only depends on the roughness. And it turns out that if you see how it scales with the roughness, it goes as roughness to the power 1/3. And that's called the Strickler law. So the question I want to ask now is this evidence of a critical phenomenon? I'm going to show you that it is. Just like the 2 stylized facts I showed you for the magnetic phase transition at the beginning of the talk, we can take these 2 stylized facts, and these turn out to come from a critical phenomenon. So let's just go through that. So what I've shown you at the beginning of the talk was that turbulence and critical phenomena share some features in common. In particular, they have power law correlations At the critical point, mean field theory gives power law correlations for the order parameter, and the Kolmogorov's theory gives you k to the minus 5/3 power law scaling for the velocity fluctuations. I showed you the large-scale thermodynamics and the phenomenon of data collapse. Remember this curve here that I showed you a few minutes ago, where all the magnetic data for different materials all fell onto one universal curve when plotted in the correct way. So we're going to ask ourselves, what is the analog of the data collapse for turbulence? And the answer is this. When you think about the data collapse for the large-scale thermodynamics, you're looking at the magnetization as a function of external field and temperature. For turbulence, the analog of the external field is something that induces turbulence, in other words, the roughness of the pipe walls. So when you go and work out the analog of Kadanov's block spin arguments, what you end up with, and I'm not going to go through the analysis, is that the friction factor should be this function of the roughness divided by the radius of the pipe times the Reynolds number to this particular exponent here. And you can read about this in my paper from 2006 and Marfan and Portolano's analysis of the data in 2008. So what they showed is that if you generalize my formula to include the intermittency correction, these data here beautifully collapse into these data over here. And so what I've just shown you then is that it's as if there is a critical fixed point at Reynolds number equals infinity, roughness equals 0, which controls the frictional drag properties of turbulence above the laminar-turbulence transition. So now we've completed this table here, and we've discovered the analog of the Widom scaling from critical phenomena, the analog of Widom scaling in turbulence. Now this is really quite fantastic, because what it says is this. Back in 1933, Nikoradze, who knew nothing at all about critical phenomena, goes and measures the pressure drop across a pipe. And just from that measurement, if you know critical phenomena and so on and so forth, you can deduce the anomalous dimensions of turbulence, the intermittency corrections. So, and you can do that. That measurement was done 8 years before Kolmogorov even guessed the mean field theory scaling of turbulence. So I consider myself very lucky that I was perhaps the first statistical mechanician who ever looked at these data and had the opportunity to work out what the implications were. So what I've shown you then is that from the friction factor, we can deduce the intermittency corrections to velocity fluctuations. And so we've seen a connection between the velocity fluctuations at small scales and the friction factor or dissipation at large scales. And that is, of course, a fluctuation-dissipation relation. Now, where do these exponents come from? Well, one can also make progress on that too. In a physical review letter back-to-back with my paper, my colleagues at Illinois, Gustavo Joyo and Panaki Chakraborty, made a kind of mean field theory argument, which is heuristic, of course, and I'm not going to go through it. But what they ended up with was a formula that says the friction factor, the dissipation, is proportional to this integral of the energy spectrum, and the limits of this integral reflect both the roughness of the walls and the Reynolds number in the way shown over here. And I'm not going to go through the argument. And so this is a prima facie dissipation fluctuation relation. And from this, if you just plug in E of k as k to the minus 5/3, you can deduce the Strickler and Blasius laws. Now, how can we test this? Well, it turns out you can test it in 2 dimensions. And you can test it in 2 dimensions because in 2 dimensions, there are 2 cascades. There's the forward, there's a cascade from large scales to small scales, just as there is in 3 dimensions, but that cascade is not of energy. It's a cascade of angular momentum, or actually more precisely, vorticity. It's known as entropy. And that 2D forward cascade turns out to have an energy spectrum, which up to logarithms goes as k to the minus 3. It has a different power law here because the vorticity of a flow has different dimensions than energy. But there's another cascade in 2D, which is that the energy flows from small scales to large scales. Something like you might think is related to, say, the stability of the big red spot of Jupiter. Not quite that, but something related to that. And because that's a flow of energy, that has the energy spectrum k to the minus 5/3. Now, the formula that we have that connects the friction factor to the energy spectrum just depends on what the power law form is for this energy spectrum. And so we can easily work out what is the prediction for the entropy cascade for the friction factor in that regime. And the answer is it should go as Reynolds to the minus 1/2 in the Blasius regime and roughness to the 1 power in the Strickler regime. Whereas in the inverse cascade, you have the same exponents that you do in 3 dimensions. So we tested this by teaming up with Walter Goldberg in Pittsburgh and Hamid Calais in Bordeaux. So here's the experiment. It's a soap film held between nylon wires as shown over here. The fluid is injected at the top. It has got particles in the flow that reflect light. You fire a laser beam at it so you can do laser Doppler Wall symmetry, and so you can measure the velocity field in this flow. You put rough walls on the pipe as shown over here, this 2-dimensional pipe. And from that, you can then create the 2 different types of flow that I showed you. So here in this geometry, where you put a fork in the flow, you have an energy flow that is a forward cascade of entropy. And you can see the k to the minus 3 power law shown over here as predicted. If you do this geometry, as shown over here, where you have one rough wall, no fork, no grid in the pipe, and something smooth on the right-hand side, you get an inverse energy cascade going as k to the minus 5/3, as shown over here. Okay, so now we can create these 2 flows. And now the question is, in those 2 flows, what is the wall stress? What is the friction exerted on the wall? And here's the data, and you can see that the friction factor, as a function of Reynolds number, scales as the minus 1/4 exponent when you have the energy inverse energy cascade, and it scales as Reynolds to the minus 1/2 when you have the forward entropy cascade, as we predicted. Just in the last year or so, Hamid Calais and Pinaki Chakraborty and collaborators were able to extend these measurements beyond the Blasius regime into the Strickler regime, where the dissipation comes from the rough walls. And you can see here the friction factor as a function of the wall roughness scales as the first power, just as predicted. And here is the universal scaling function. This is the analog of the Widom scaling. This universal, the data plotted in this universal way, which should collapse onto one universal curve if this whole idea is right, and you can see that it does. So what we've learned from this then is that the drag experienced at large scales reflects the very nature of the turbulent state at small scales, and we make 2 predictions, both of which were confirmed experimentally. Actually 3 predictions, to be honest. Okay, so now I'm ready to conclude. So what I've shown you is that there's 2 types of universality in turbulence. One is the transition to turbulence, which is a non-equilibrium phase transition in the universality class of directed percolation. And then the flow above that transition in a fully developed regime is controlled by a critical fixed point at Reynolds number equals infinity, roughness equals 0, a singular point, if you will, which controls the fluctuations and the drag. So here are the people who did the work with me: Hamid Calais, the late Walter Goldberg, Gustavo Joy and Pinaki Chakraborty, now at the Buchanan Institute, and Tuan, who's now at professor in Singapore. And this is Hongyan Shi and myself in the basement of the mechanical engineering department at the University of Manchester, where you can still see Reynolds's original apparatus. This is Tong Si, who was an undergraduate who worked with us, and this is Shiying Wang, who is a graduate student with me now, who worked on the spreading of slugs, which I didn't really have time to talk about. Let me end with a fortune cookie. This is a real fortune cookie that I actually got, and I am probably the single best person in the entire world to get this fortune cookie. Why? Because it says turbulence is a life force, it is opportunity, let's love turbulence and use it for change. And for luck, it gives you some numbers that you can use in your Monte Carlo simulation. Now, the point about this is it connects turbulence with life, i.e. biology. Now, in many talks, you say from a biophysicist, somebody will come along and say, look, I've built a microscope, a special microscope using some very clever physical ideas, and so I can help you see, super resolution structures inside a cell, or I can do a better computer simulation using molecular dynamics and so on. So you can use physics to solve biology problems. But here, in the story I told you today, we used biology, ecology, in fact, to solve a physics problem. In fact, the student who was working with me, Hong Yanqi, her first problem was to try to understand evolution in microbial systems subject to invasion by a viral predator, and looking at the evolutionary dynamics of that and so on, using stochastic methods and quantum field theory and so on, which I'm not going to go into. Her physics problem, part of her PhD, was working on turbulence, and halfway through the PhD, we discovered that these problems were actually the same. So anyway, I'll leave you with that thought. Here are the references, and I'll be happy to take any questions.
Thank you, Nigel. That was really, really interesting. Just while people are formulating ideas, actually, I can probably go to the Q&A panel straight away and we can get started. So Jorgen Fredrickson gives a quote, Martin, Sigge and Rose, 1973, the whole problem of strong turbulence is contained in the proper treatment of the vertex renormalization. Do you have any comments about that? Observations?
Well, that's talk is cheap, is what I would say. So I would say no. Because the problem is you can't really solve this by perturbation theory. People did actually try. Jacobs and Orszag tried to do that. I don't think it's quite as simple as just saying take the Navier-Stokes equation, stick a fluctuating force on the right-hand side, and then see what you get. So I don't really quite agree with that statement, although I understand the spirit in which they were saying it. On the other hand, I will say that if you look at the transition to turbulence, which is not what they were talking about, Martin, Sigge, Rose were talking about fully developed turbulence. In the transition to turbulence, I do basically tend to agree. You can write down the predator-prey vertices as I showed you, and indeed, you can actually go ahead and calculate vertex renormalization and so on and so forth. And indeed, all of these things are important.
All right.
Thanks for a nice question.
And then he had a follow-up question. Could you let us know where your Feynman diagrams for the zonal flow turbulence model have been published?
Yes. So the work on this is this paper here and this one here. These two papers. And then we have another paper that's just about to come out in physical review letters. It's not terribly helpful. I mean, the work that we did, we didn't try to understand this by perturbation theory, because there's no need. Once one's written down once one's seen the diagratic calculation, then the Feynman diagram part, we actually can just use work that was already done by Mauro Mobilia and Uwe Teuber in 2007. And so the paper I would refer you to is Mobilia et al. 2007. And I definitely recommend a beautiful paper by Uwe Teuber in 2012, which was basically a review article showing how you use Feynman diagram analysis to look at these stochastic predator-prey systems. So it's exactly the same analysis for that as here.
I just wanted to clarify something. On the slide you had showing the decrease in the size of the vortices in the cascade region, I believe you said it was. Is that, are they diminishing in intensity with time, or just decreasing or are they becoming smaller and also weaker? I wasn't sure about that.
The energy that is contained in them as you go to smaller scales gets less and less.
Right. Okay. I was just wondering whether that could be related to the formation of tornadoes.
No, it's not for that reason. But I think there is a connection with tornadoes, and actually, it's one of the things that I haven't yet completed, I haven't yet done, but I would like to, which is this. I think that the formation of tornadoes, tornado genesis, it's a significant problem, because when you try to just simulate, say, hot and cold air, the usual explanation that you see about tornado genesis, it doesn't really give you the right frequency. Tornadoes occur more frequently than that would predict. And I think there's a piece of physics that's missing. And the critical piece of physics that's missing is that the question is, what is a tornado? And the answer is, what a tornado is the absence of turbulence. So if you ask what controls the speed of an atmospheric flow, the answer is, let's say you take a river and it's flowing from a mountain top down to the sea. And you might say, well, how fast does the river flow? Is it the, potential energy gets converted into kinetic energy at the bottom? Well, that's way too fast. Then you might say, well, is it just the viscosity? Well, again, that doesn't give you the right answer either. It's the turbulent drag that controls the flow of a river, and similarly the flow of an atmosphere. Now, what happens is when you have rain or you have dust, say like in a dust devil, what that does is that suppresses turbulence. You have to use kinetic energy to elevate the suspension. And so the suppression of turbulence will then increase the speed. So what's happening then is that the things that you want to understand about a tornado is, first of all, why are the wind speeds so high? And secondly, why is it so localized? And both of those things can be understood by thinking of the tornado as a flow, which is the boundary between laminar-turbulent, which you can show is a sharp boundary, and it's caused by the suppression of turbulence leading to the high wind speeds. Of course, there's a bit more to it than that, but that fundamentally is the sort of root of what I would regard as a sort of poor, a sort of first pass of a theory for why you get tornadoes in the first place and how you get qualitatively the phenomenon.
Fascinating. So I just wondered if you could say a little bit more about the relationship between the inertial range, the Kolmogorov -5/3 law, and the cascade region that you talked about. Just exactly how those three things are related a little bit. You probably said it, but I may have just missed some of the details.
Okay, how you derive the spectral properties, k to the -5/3 or whatever, from the picture of the vortices, as it were, the swirly whirly eddy things. That's really what most people have tried to understand, the mechanistic origins of that. It's still not understood. For many people, if you say, what is the problem of turbulence, it would be to exactly do what you just said, connect those fluid motions to that particular scaling law. And so the beauty of the sort of field theoretic scalings is that you don't have to really be terribly specific about the types of flow configurations, just like in a magnetic system. You don't have to do that. So that's a part where I think many people would say that's where we really don't understand as well as we ought to be able to, and I agree with that.
Okay, Dimitri, Efimkin would like to know, is it possible to connect the coefficients in predator-prey model and the Euler-Hydro equation, at least up to orders of magnitude?
So you want to know, so let's see, what are you asking? You're asking, can you connect, well, I would say, yes, you should be able to, in principle, but in practice, you never do. After all, in magnetic systems, you can't really calculate the coefficients in the Landau free energy from the microscopic theory of the magnet. And the whole beauty of the renormalization group is that you don't need to, because what happens is as you scale to closer and closer to the critical point, these coupling constants go to fixed point values. And so not being able to calculate be able to relate those different models isn't a drawback. It's a feature, if you will. So it would be hard to do, and I certainly don't know how to do it. Now I do know how to do it in mean field theory to some extent. So in a paper I wrote in Journal of Statistical Physics in 2017, where I give a sort of mean field argument that explains how to start off with, say, Navier-Stokes equations and derive a kind of predator-prey mean field equations from that. So that's the place I would direct you to. Right. And that's really following Pat Diamond's arguments, which were done in the context of magnetohydrodynamics.
Right. Matt Reeves has a question: is the critical value of RA sub C for percolation sensitive to upstream disturbances? And then he writes, I recall reading somewhere that modern versions of Reynolds' experiment at Manchester got different values to his original experiment due to vibrations caused by road traffic.
Well, that's probably true. Again, if you have vibrations, the Reynolds, the point at which the Reynolds number, where you get the transition, does change. And if you've got a very smooth system, then it doesn't. You can keep it laminar up to a very high Reynolds number. So yes, it's very sensitive because it's a subcritical transition. Any vibration, you just hit the pipe, it'll make it go from laminar to turbulence.
Right. Kyrillos Iskander wanted to know, and I was kind of interested too. I don't know how much time you've got, but if you could just spend a couple of minutes talking a little bit more about the slug spreading that you glossed over. But I don't know whether you've got time to do that. If you have to shoot off, that's okay.
So yes, I can. So I'm sorry. We have a sort of domestic problem here due to a skunk.
Oh no!
I'm going to have to go.
That's all right. That's fine. We can do it another time.
But tell me, what was the question that you?
I think it just like a little bit more information about the. You said you couldn't really talk about it. You had to gloss over the.
I can do it. I can do it in like 2 or 3 minutes. Is that okay?
Okay. Yeah. Sure. By all means. If you have to go, that's fine too.
Well, even if I go, there's nothing I can do because our whole house smells of skunk.
Oh no! Oh, that's terrible.
I think our dog got skunked. So.
Oh no!
Live on YouTube. Okay,
it's easy for us to laugh about it. We're not there, right? So.
Yeah, that's right. I don't know what we're going to do. All right. So yeah. So let me just answer your question very quickly as best I can. So here's what I wanted to show you. So the slug spread above about 2200, something like this, is shown over here. So the question is, what happens if you couple the puffs? So one answer to that was provided by Dwight Barkley about 10 years or so ago. He guessed that the way that the turbulence would behave would be kind of like an excitable medium, just like you have in a nerve fiber, and he made a sort of a model, a phenomenological model, to try to explain the behavior of turbulence like that. When we couple these things, what happens is that you actually end up also being able to get a phase transition between different regimes of puffs, spatial-temporal intermittency, slugs that spread with one front, but no front on the downstream side, and then slugs that have 2 fronts on both upstream and downstream side. And mathematically, these 2 descriptions turn out to be the same. Again, that's a whole other seminar that I'd have to give you to explain that connection. And one of the things, yeah, I just don't have
That's fine. We can see the reference at the bottom of that slide, so we can look it up.
Yeah, it'll be it'll be coming out in physical letters in the next couple of weeks.
That's great.
So anyway, I am going to have to.
Of course. Thank you very much, Nigel, and thank you everyone for attending. And we'll let everyone know when the next seminar is coming up. Thanks again, Nigel.
And yeah, somebody just asked, is it possible for me to share the slides? And the answer is yes. I'll send them to David. Just send me an email or something.
Yeah, and I'll just follow that up with saying that you'll be able to watch the presentation again on YouTube. So you'll be able to see all the slides there if you need that urgently. So it should be up within a couple of days.
And I'm happy to share them too.
Oh, thanks, Nigel. Marvelous. Well, thank you. Thanks very much again. Thank you, everyone. We'll leave you to your domestic problem.
Thanks.
Bye for now.